everybody. Yay! Hello, hello, hello. Everybody who knows me knows that I'm a stickler for starting on time. Hi, welcome to Yue Qin, our speaker for today, and to everyone for coming. We're glad to see you on this very rainy January day. Just short introduction, most of you know her, we hope. So she joined us last fall as an assistant professor in this department, also with an appointment in the Discovery Themed Sustainability Institute. So Dr. Qin has research interests in coupled natural human systems, the food, energy, water nexus, and air quality, human health, climate, water linkages. So I assume we're going to hear about some of these today with regard to her current research. So she received a bachelor's degree in engineering and environmental engineering from Beijing Normal University, a master's in science and environmental science from Peking University. Both of these degrees were with first-class honors. And then her PhD, 2017, from Princeton in science, technology, and environmental policy. Then she went to UC Irvine to do a postdoc before she came here. Has already got a very substantial publication record with papers in PNAS, Nature Sustainability, Atmospheric Chemistry and Physics, and other top journals. It's also my pleasure to announce, I forgot to put this in the weekly update, so what will be there next week is that she's just won an Early Career Award.
Oh, wow.
It's the Yue Qin Early Career Award from the Chinese American Oceanic and Atmospheric Association. So yeah, so it's really a great honor. So we're very lucky to have her with us, and we're glad to hear more from her today. So, thank you.
Thanks, Donna, for the introduction, and thanks everyone for coming on rainy January day. So the title of my talk is about the air quality, climate, and water implications of energy and agricultural development. Because our speaker series is on urban Asia, so I will mainly focus on the energy transition in China today. And I will briefly introduce some of my related work on the agricultural development. If you are interested, I do have another talk at the Bird Institute this semester, and you are more than welcome to join that one as well. So going back to our talk today, how many of you have ever been to China? A lot of people. So depending on when and in which season you were there, you may be impressed by what you see, or you may be really shocked by what you cannot see. So regardless of whether you have ever been to China before, you probably heard about the severe Beijing Smog breaking out in 2013, which was widely covered in both domestic and international news reports. So within the country, the citizens have been taking a lot of protection measures for themselves. And also, let's create some business opportunities. Can anyone make a guess what's inside?
Fresh air.
Fresh air. Yeah, it's fresh air for sale. So, not only just the locals, the international school of Beijing also spending like billions of money to build some domes to ensure healthy breathing of the air. So obviously, air pollution in China is a huge issue. Here I'm showing a global map to show the annual average PM10 concentrations over 1,000 cities. So if you look at the PM10 concentrations in the US and compare with that in China, we have much better air quality here. However, it's also worth mentioning the air pollution problem is not just a problem for China. It's actually a common issue across the world in many less developed countries at least. And China is actually one of few countries that have been taking progressive measures to combat the air pollution problem. And also, the lessons we learned from what China has been doing maybe provide some valuable experiences or lessons for other developed countries or cities. So what has China been doing? Actually, In early 2014, China's Cup official premier Ke Qiangli made a strong announcement at the open ceremony of the annual meeting for the parliament to say we will, as I call it, we certainly declare war against the pollution as we declare war against poverty. So this is basically from the highest government official and to make a strong statement describing the smog as the nature's red light, warning against inefficient and blind development. And it's the acknowledgement from the highest level there is a crisis. To make this worse, air pollution isn't the only problem is facing China today. There are many multiple environmental problems in addition to air pollution, such as global climate change, which is likely to cause increasing sea level rise that is threatening China's many east coast cities. Also, it also suffers from severe water stress issue with only 1/3 of global average per capita water resources. Among all these environmental problems, behind all of them, there is actually one common reason, that is China's coal-dominated energy structure. Here I'm showing the historical energy consumption by fuel types from 2000 to 2015. As you can see, up till 2015, this coal still accounted for about 64% of China's total primary energy consumption. In comparison, the cleanest fossil fuel, natural gas, only accounted for 6%, with other hydro and petroleum making up the rest. This number, the coal percentage, I believe recently, for the first time, went below 60%. So right now it's about 58%. Even though it's not like significant from the share, but think about it, China as the world's largest energy consumer. So 1% of energy structure changes, energy consumption would be at the same scale of the national total energy consumption at countries such as Norway. So it's huge. So obviously, Chinese government and even Chinese citizens are aware of the problem caused by coal. So they have been taking efforts to move away from coal. One strategy that has been taken is to invest in renewable energy. Despite renewable energy might be the ultimate goal for our future energy system, but there are right now it's just tiny. With the wind, it's about like 2.5% of the total primary energy consumption share, and the solar is only about 1.2. So there is no way they can quickly ramp up and substantially substitute for coal and to reshape China's energy structure in a short time, particularly with many intertwined and complicated problems such as intermittency issues, high economic costs, insufficient energy storage, and also underdeveloped infrastructure. At the meantime, every year, there are about 1.2 million premature deaths associated with air pollution within China every year. So that's more than the whole population in Columbus. So obviously, we cannot wait for renewables to scale up and then to see what we can do with coal. So another strategy the Chinese government has been doing is to move away from coal to natural gas. So compare the way the coal combustion, natural gas combustion has some advantages. For example, it emits almost no PM or sulfur dioxide. When it burns, it emits roughly half of carbon dioxide emissions. And also, it significantly reduces the cooling water consumption. So another important reason is that natural gas actually has a potential to ramp up relatively more quickly by coming from a variety of sources such as conventional natural gas from onshore and offshore gas fields, also the imported pipeline gas from Central Asia and Russia, the imported liquefied natural gas, as well as domestic unconventional natural gas, including mainly shale gas and coal-based synthetic natural gas. So we all know that both energy production and consumption will simultaneously affect the air quality, climate change, and water stress. So depending on where and how we obtain the energy sources and where and how it's consumed, this may cause synergies and trade-offs among different environmental impacts. For China's purpose, there are 6 major gas sources, as we showed in the earlier map. Also, if it can be used to substitute for coal, there are 3 major end uses that can potentially happen. And we focus on the 3 environmental impacts that we are mostly concerned about. I will first give you an example of the coal-based synthetic natural gas to see what its environmental implications. For people who are not familiar with coal-based synthetic natural gas, which we call SNG for short, basically it means we take advantage of abundant coal resources in Western China and go through some chemical process as gasification and methanation to produce SNG. And then the SNG produced, which essentially is natural gas, will then be transported to Eastern China, where we have large high population density and large energy demand, to replace for coal combustion. Because gas burns much cleaner compared with coal, so it can be used to improve air quality. But also because we have to go through 2 stages of energy conversion, firstly from coal to produce natural gas, and then use the natural gas either for cooking or for electricity generation. These 2 stages of energy conversion will need to increase the life cycle carbon dioxide emissions. So the deployment strategy matters in terms of how can we best use this produced SNG in order to bring as much as air quality and human health benefits as possible, but at the same time try to minimize the climate penalties. In order to answer this question, we integrated spatial simulations and integrated assessment model framework. We firstly designed some scenarios for SNG deployment and then use a GAINS model to calculate the air pollutants changes due to the different energy substitution scenarios. Then we use a regional atmospheric chemistry model, to simulate the grid level PM2.5 surface concentrations. Finally, we integrated with the integrated exposure response functions to estimate the associated health impacts under each scenario. So here is what we get. As here it shows the reductions in annual average PM2.5 surface concentrations under 3 different scenarios. And obviously, under the residential allocation scenario, that's where you observe the significantly larger PM2.5 reductions, and particularly in the most populated and energy demanding Eastern China. We take a further look at its seasonal profile and find the largest reductions occur in the dirtiest winter season. That's mainly for the heating demand to burn coal, and when you can replace that coal, you can significantly reduce the emissions and improve the air quality. So going back to the question we asked a bit earlier, it's not only a problem about air quality, it's also a problem about the carbon emissions, greenhouse gas emissions, and climate change. So we integrated the number of avoided premature deaths together with the life cycle carbon dioxide emissions together. So basically, the x-axis indicated how many, it's kind of how many people's lives you can see. And a larger number means more people will be avoided from premature death. And the y-axis would be the net changes in carbon dioxide emissions. The higher magnitudes indicate higher climate penalties. So what we can observe here is, firstly, under all three allocation scenarios, basically you all achieve the air quality and the human health benefits, but all at the expenses of increased carbon dioxide emissions. There is an obvious trade-off. However, among these three scenarios, the SNG residential scenario, which indicates we mainly replace coal in the residential sector, helps to bring the largest healthy improvements and also leads to the noticed net increases in carbon dioxide emissions. So it's kind of from both air quality and climate perspective, it probably makes most sense to use SNG in the residential sector. It's possible to change the picture and bring air quality and climate co-benefits if we can use technologies such as CCS, which is short for carbon capture and storage. However, even with CCS, it still emits like 20 to 40% more carbon dioxide than the same amount of conventional natural gas. So our general recommendation from this study is basically SNG is probably not the best energy, like alternative energy source, even compared with coal, because it achieves the air quality benefits at the global climate expenses. And for the existing SNG, the best way to use it is probably in the residential sector. So we take a further step to ask, because we know there are more than SNG, there are multiple energy sources and there are multiple end-use decisions, and we kind of try to improve both air quality, climate change, and water stream. So we made an effort to integrate all potential gas sources and try to design different energy deployment strategies, either by maximizing air quality improvement or maximizing climate change mitigation in terms of greenhouse gas emissions, or eliminating the water stress the most. And we asked the three questions. First is, what are the air quality, climate, and water impact under different source choices and end-use decisions? And the second question we ask is, what are the interactions among the three environmental impacts? And also, we try to understand what's more important, source choices or end-use deployment strategies. So here is a busy figure, but the key message here is basically, as you can see, the different colors indicate different gas sources. X-axis shows the changes in PM2.5 concentrations, which indicates air quality improvement. And the y-axis shows the changes in life cycle greenhouse gas emissions, which indicates the relative improvement in climate, slowing down climate change. And the shapes actually indicate, shape sizes represent the absolute changes in weight and water consumption. And when it's a solid shape, it indicates increases water stress. And its open circles indicates decreases water usage. So what we find is, under mean methane leakage rates, basically except for SNG, all gas sources achieve air quality, color, and water co-benefits. So SNG is really the only one that achieves air quality benefits, but only at the climate penalty expenses, also at the local water stress expenses. what's more importantly, we integrated that with the spatial analysis, which find not only it results in national total increases in cover and water both dimensions, it also happens in the regions that already suffered from the severe water stress and the highest per capita carbon dioxide emissions. So it's kind of making things worse in places where it's already suffer a lot. We also find that even for the other gas sources which will actually help to improve both air quality, climate and water side, there is still a trade-off in terms of the magnitude of improvement. Which means if you look at it, there's circles here, when they can achieve relatively large air quality benefits, but the water benefits are tiny. And the same thing happens when we are water focused, you can achieve large water benefits, which is indicated by the size of the circles. But those air quality benefits are almost negligible. This is mainly because the geographic mismatch of regions with high water stress and severe air pollution, and also the sectoral variation in terms of the magnitude of improvement you can make. For example, when you are mostly water focused, we find most of the substitution will happen in the power sector, where you can help to save cooling water consumption by switching from coal to natural gas. But power sector in China is actually under good control. So there are a lot of end-of-pipe controlling technologies already. So the relative air quality improvements are relatively small. And when we are air quality focused, we find that most of the substitution occurs in the residential sector, where you can achieve significant air pollutants reductions, but you don't actually observe much water improvements. And the third question we ask is, which factor, sources or end uses is more important in affecting different environmental impacts? So we actually find for air quality, end use, so that's basically how you use the relatively clean energy, or how do you do the substitution matters the most. It's actually a magnitude higher in terms of the air quality improvement compared with the differences among gas source choices. But for cover and water impact, the sources is really the key because of SNG. So that can completely change the direction of whether you are improving or making things worse. Other than SNG, for other gas source types and end uses, we find still end uses can be relatively important, even compared with gas source choices. So what are our major conclusions from this? So what we find is China's switching from coal to natural gas strategy basically can benefit air quality regardless of gas source choices and end use deployment strategies. But it may actually increase carbon emissions and water stress depending on where you get that natural gas. So it's really probably important to at least limit the scale of SNG development, which is not only bad for global climate and also not a good thing for local water stress issues. And we also find, even though there have been a lot of discussions on developing renewable energy, which is important, it's also sometimes important to think about what's the best way to use the clean energy and what's the best way to substitute the coal. So where to do the substitution, and also also the key in determining the air-water trade-offs, which means even though for source choices or end uses, it can simultaneously improve air quality, climate, and water, there is still trade-off in terms of how significant the improvement can be. So you have to make a localized decision to prioritize the most important environmental challenge. To summarize the title of a report covered our paper, so I feel it provides a good suggestion. Basically, it really requires integrated and strategic approach to balance the air quality, carbon emissions, and water scarcity goals. And we believe this can be some valuable experiences for other developing countries which are going through or might go through similar energy transition pathways. So what I have been thinking on this whole energy transition thing, I remember I showed this figure in my earlier job talk last year, actually also around this time. So basically, I've been really intrigued by the interactions among the energy system, human society, and the natural environment. And the first question is, what other environmental and human society impacts due to energy transition? In one of my earlier work, I built up a global thermal power plants database for cooling water consumption. So one of my projects I've been working on is try to figure out the global, at the global scale, the water stress due to decarbonization of the power sector under the shared socio-economic pathways based on unity level carbon-water trade-off analysis. So basically, we are trying to see, even though decarbonization is important to slow down climate change, but we also have to make sure we avoid some unintended consequences and build co-benefits for other dimensions at the same time. This is particularly important for regions that are already under severe water stress globally. Another is more like something in my head. I've been thinking about it is I hope to build some collaboration, particularly within China, to get some high resolution data for the power generation and demand. So we can use some optimization model to really evaluate the impacts of renewable energy and how could that help to improve the environmental challenge, to help us address the environmental challenges. So yeah, I guess I'm particularly interested in something like how electrical vehicles will help to facilitate the integration of renewable energy, something along those lines. Yeah, still thinking about that. And a similar question is, what other environmental impacts due to human society development? On this topic, I'm more thinking about the urbanization process. So basically, how urbanization will change the human energy demand, the consumption, both at the individual level, communities level, and business structures. So that's also something I've been thinking about, but probably need to spend more time to really dig into that. And as I mentioned, I will briefly introduce some of my work related to global food, energy, water nexus. So I have a paper published last September on nature sustainability, which is also picked up by Nature Research Highlights. So basically, the previous work on water stress has been focusing on the relative share of water that is being consumed to indicate how severe water stress is. But what has been missing is they didn't differentiate the flexibility of different water uses. So basically, when facing drought, some water uses mitigation are easier or have lower socio-economic costs. So it's relatively more flexible. And some water uses, for example, if you think about it, are basic human water demand or cooling water for electricity generation or for perennial crops, those things are relatively more inflexible. So we build up data set for water uses and intensities in the past 4 decades. Here is an example of the irrigation annual and perennial crops water consumption, which we collaborated with agriculture scientists to build the global crop water model and provide crop-specific grade level monthly irrigation water consumption. And another project I've been working on is more from the climate adaptation side. It's about agricultural risks to changing soil melt. Basically, we are trying to reconcile the sub-annual snowpack and runoff dynamics with the unique timing and magnitude of agricultural water demand. Try to identify the global hotspots where irrigated agriculture has been historically depending on snow melt runoff as water sources, and which may be particularly vulnerable due to changes in terms of both the magnitude and the timing of snow melt runoff under climate change. So we have been working with some snow experts and climate scientists to get the data. So here is one figure to demonstrate. So basically here I'm showing the San Martin Basin, and the red line indicates the rainfall runoff, blue line indicates snow melt runoff in the baseline of warming scenarios. So as you can see, under a warming climate, there is an upwards decreasing and also early shifting in the snow melt runoff. The rainfall runoff actually increases under the warming scenarios. However, if we bring the water demand into this picture, you can see even the magnitude of increases in rainfall runoff can compensate for the decreases in snow melt runoff. It doesn't occur in the same season when water demand is most needed. So there is not only a magnitude mismatch, also a temporal timing thing is also important. So that's basically what we have been trying to figure out. And the purpose, as I mentioned, is try to identify the global hotspots that are mostly so dependent and also vulnerable on the climate change. So yeah, this is the other work I've been working on. Some other thoughts on this agriculture side, where right now I'm also trying to work on integrating the snow work with some global food trade work. So try to see the virtual water transfer into food trade and how the future maybe climate change or other changes are affecting these trade patterns and affecting the water stress as well. So those are what I have for today. And at the end, just I probably should go back to
Where's the San Joaquin Basin?
Oh, California.
Have you identified other places in your last slide, like some other places that are vulnerable because of the snow melt rainfall? Or, I mean, I know you're working on it, but are there other places that you know of, or?
Yeah, there are, if I remember it correctly, also another hotspot would be in the Tibetan region, so the high regions in Asia. Yeah, that's another place.
Do you think that might be the case in the Andes in South America as well?
That's definitely one part we identify the relatively high portion of snow contribution to irrigation water, but I can't remember exactly whether it has significant irrigation water demand at the first place. So yeah, so it basically depends on two things, like how the relative share of snow in contributing to your irrigation water, and you need to have like at least or decent amount of irrigation water demand, so you have to have crops there.
There is so much amazing stuff in here. Thank you for the food for thought. Something with the natural gas and renewables and comparing different possible policy approaches. can you comment a bit on the question of like infrastructural inertia and the idea of, so like if next year everything switched to this or that kind of natural gas, certain benefits would be achieved, but is there still a longer term cost because that forecloses the development of more renewable energy sooner? So is there like an infrastructural lock-in problem, or maybe there's not?
So that's a great question for a few things. The first thing is, I think the first thing I would like to mention is we talked about it's probably difficult for renewables to ramp up really quickly. Like say the energy infrastructure, say pipelines might be operating for 20 or 30 years. I don't know. Yeah, probably around that time scale. But for renewable energy, it probably won't be completely or to if we don't have a technology breakthrough, so it probably won't be like in a short time to really cause any like shifting of the energy structure and making the natural gas infrastructure be a complete waste. And the second perspective is, I think one advantage of China is it really has high efficiency in terms of building up infrastructure and unfortunately also destroying infrastructure. Which is a bad thing, but to answer your question, that's still, I mean, we have been seeing a lot of things like retrofitting the coal generators to natural gas generators or to other generators. And the Chinese government has been demonstrating a really capacity in destroying the infrastructure at the same time. And the third thing, I think another question to ask, whether there will be competitions in terms of the investment on natural gas or renewable energy. From my own observation, I think the answer will be no, because like the Chinese government is so determined to develop, like to move away from coal, and right now they really want to like spend more money. They have the economic capacity, and they are interested in spending the money to develop the energy structure for many different reasons. And for renewable energy, also a lot of incentives from the industrial side. So it's not just the air quality issue as well. So I would say there are enough or sufficient economic capacity to invest on both dimensions. But I mean, that's my own perception.
Yeah, just following up on that, because I have similar questions to Sam. I was really struck by the slide that you showed of who was deploying resources to invest in renewable energy in China. And when you're talking about the Chinese government being strategic about moving away from coal, and like how does that sort of play out of who they're willing to partner with? Because the biggest investor was China, but then there was some really interesting kind of regional.
So you mean like within China?
Yeah, like who's going to invest into renewable energy?
So for renewable energy, particularly for solar, as far as I know, there are many actually like small private companies. And the Chinese government initially provided subsidies to those companies. So solar, especially solar panels construction, have been like going like really ramp up quickly, and it significantly brings down the price. For wind energy, I'm not sure. Like there are still a lot of like for all renewable energy, there are many more private companies involved compared with the traditional fossil industry. That's my impression. But still, the grid company and the power generation, state-owned power generation companies are also starting diversifying their profiles at the same time.
It's fast. So it's interesting if energy, climate, pollution, right, could drive structural change in the economics of energy.
For sure. I guess it's not the only. I think the fundamental motivation is probably not just the air pollution. Like air pollution is one important issue among many other important issues in terms of renewable energy. There are also incentives from the industrial side to take up the market and and to be a leader, technology leader, to take future market as well.
Does your model for the natural gas, greenhouse gas emission stuff, does that account for changing total energy demand within China?
No, so basically we are fixing the energy demand. So whether you are using coal or using natural gas, so it's just in like which energy source you use to supply that demand, to meet that demand.
I'm curious on the natural gas thing. There's an apparently quite strong effect in switching to natural gas for residential air quality, especially improvements of air quality in the residential sector. So I was curious how, can you differentiate because the maps show that encompass rural and urban areas, and so I'm curious if there's differences across these two sectors, and the reason why I work with these two areas, because part of the reason I ask is because in the cities, there's, I could be wrong about this, but it seems like there's greater facility to introduce and to lay down pipes and to bring piped gas into homes. And it's more difficult in the rural areas, where in fact coal for heating and cooking is much more common. So does the model account for that in the variation between the different actual uses in urban and rural areas?
So that's a great point, and you are 100% correct. Most of the natural gas is still used for urban settlements, not really much go to people. Things may have been improved, but slowly. But as you mentioned, in those villages, it's really difficult to build the pipeline infrastructure. It's so expensive, much lower population density. So most, and also even for citizens, domestically, they're still insufficient. Insufficient in the way we still want to use more natural gas in the residential sector. So there are still not every city are using natural gas in the residential sector for cooking and heating. So most of the natural gas currently in the residential sector are deployed for urban settlements. And in terms of our model, I don't think we can account for really differentiating whether it's used in urban citizens or people in the villages. We don't actually differentiate that because most of that, as I mentioned, is in the urban settlements. So yeah, so the energy demand and substitution within the province, we don't differentiate.
I want to talk about switch topics to this snow melt runoff and rainfall. And we're facing a different issue here in the Midwest, where we're going to see more rainfall overall, but also more drought. And in the Cura panel we had earlier today, one of the panelists pointed out that that's going to make growing crops more difficult in this part of the world because we're going to have more, less certain conditions, less constant conditions, more intense rainfall events with longer drought periods. So I'm wondering if you've considered that, or you are considering those type of issues, because this is something we normally haven't thought about. This is something they've thought about in the western portions of the United States, where the snow melt is a big deal. But we don't think about things like that here in the Midwest.
That's true. And actually, I didn't go into detail of our inflexible work here. In this work, we mentioned we bring out the new concept of inflexible water use, but we also integrated is the variability in annual runoff. So that basically means the inter-annual variability, so how unstable or stable or how reliable your water supply will be. So that's also one factor we integrated in our new water stress index to indicate the water stress. But even for that, it's the only account for the inter-annual variability. What you just described sounds to me is more like the extremes, like extreme drought or extreme weather patterns in terms of floods. So I think that's something also widely discussed currently in some academia fields. My understanding is there are already a lot of researchers realizing there is a problem in terms of how reliable, both on the average level, also in terms of more extreme cases, because those events can cause more damages to either to crops or to human populations, because it's more difficult to build adaptation strategies, and you have a natural uncertainty to predict what will happen in many ways. That's my
Back in the water, your last slide, the lines were availability and the bars were consumption, right?
You mean the snow?
The snow melt plus the rainfall, right? Shouldn't consumption also have a climate signal?
Yeah, that's a good point. So we basically in this work we didn't simulate the changes in water demand under climate change for many different reasons. And one important factor is there are still too many uncertainties in terms of how climate change will affect the irrigation water demand in particular, because on the one hand, probably we have urban carbon dioxide fertilization effect, which may require less demand, but when you have higher temperature. So there are some conflicting factors working in different directions.
Are they a similar magnitude, the change in temperature and the CO2 fertilization? Are they do they actually compete?
So yeah, they are compete. Yeah. So temperature, carbon fertilization effect. Yeah.
Do you have the same magnitude?
And I think there are still a few other competing factors. So yeah, so in this work we leave this factor out. But I definitely agree. We are actually trying to think about whether it's worthwhile to invest in more energy, predicting future water demand for irrigated agriculture. Basically, that's a question we will always ask.
Are you talking about a temperature-driven evapotranspiration?
For irrigation demand, yes.
I think in the beginning you showed the condition of PM10 in China, but because in the result part you didn't show the PM 2.5. So.
Oh yeah, that figure is from the World Health Organization. Basically, try to see. Try to show. I think.
What's the air pollution reduction condition for PM10? I mean, if there is some reduction of PM 2.5, but whether it is also reduced with PM10?
Okay. So first, to answer your question, whether PM 2.5 reduction will necessarily mean reductions in PM10. I think the answer is probably yes. So PM 2.5 is basically the portion of PM10 that is even smaller. So the cutting line is either 10 microgram cubic meters or 2.5 microgram cubic meters. And also the chemical process will produce PM 2.5. Whether it's primary or secondary, the process is almost the same. So it's most likely it will be the same trend. The more important thing is why do we show PM 2.5 not PM10, because PM 2.5, so the smaller size is actually more damaging to human health because it can penetrate deep into human bodies and cause COPD or stroke or lung cancer. So more related to health impacts. That's why after 2013 the smog issue happened. Before that, China doesn't have the monitor, at least the national requirement for reporting of PM2.5, and don't have a national monitoring system for that, but it's constructed after 2013. Yeah, I think those. I think I have one more thing, but yeah.
Okay, speaker once more. And thanks everybody. Join us again next week, same time, same place, for a speaker from University of California, Merced, Sapana Doshi. And thank you all. Have a great weekend.